This handsome rascal on the right here, this is Jacques Charles. And in 1783, Jacques made the first manned flight in a balloon filled with hydrogen gas. He did this about 2 weeks after the renowned Montgolfier brothers had launched the first hot air balloon. Jacques, he thought that hydrogen was better than hot air because when the air in a hot air balloon cooled, it required being heated. This required a fire, and the sparks from the fire needed to keep the air warm, often set the balloon on fire. Hydrogen overcame this obstacle. However, if you know anything about the Hindenburg, you know that hydrogen had some problems of its own. Solving problems with Charles' law necessitates that we learn about a new temperature scale. As Americans, you've grown up utilizing the Fahrenheit scale. As students in a science classroom, you've been forced repeatedly to deal with the Celsius scale, and now comes the Kelvin scale. The Kelvin scale is based upon the concept of what is known as absolute zero. At absolute zero, we have removed the maximum amount of energy possible from a collection of particles. The numerical value associated with absolute zero is 0 Kelvin. That's the equivalent of negative 273 degrees Celsius, or approximately negative 460 degrees Fahrenheit. What's really important is what appears in the middle of the slide there. You've got to be able to convert Celsius temperatures to Kelvin and vice versa. Let me give you an example. Room temperature is considered to be roughly 20 degrees Celsius. On the Fahrenheit scale, that'd be about 72 degrees. That's what most of us like our room at to be comfortable. But on the Celsius scale, 20 degrees. Well, if I said, what's the Kelvin temperature for room temperature? Well, take the 20 degrees Celsius, add 273 to it, you get 293. So right now, sitting in the room where you're watching this video, if it's a normal room at a comfortable temperature, the temperature in there is about 293 Kelvin. That's not hot, that's just a different way of expressing room temperature. Now on to Charles' law. You'll notice that Charles' law is the direct relationship between a volume of a gas and its Kelvin temperature. And you have to meet two requirements in order for Charles' law to be valid. Number one, you have to have a fixed mass of gas, and that fixed mass of gas has to be held at a constant pressure. Now we said that this is a direct relationship. What does that mean? In a direct relationship, mathematical variables travel in the same direction. When one of them goes up, the other goes up. When one goes down, the other goes down. Here's an everyday example. My age and the number of gray hairs on my head. As my age gets greater, so does the number of gray hairs on my head. So those two things are directly related. Okay? Please notice V1 over T1 equals V2 over T2. The subscripts 1 again refer to initial temperatures and volumes. The subscripts of 2 refer to final temperatures and volumes. And anytime you use Charles' law, you've got to utilize Kelvin temperatures. Our first sample problem reads as follows. A regulation football is filled to a volume of 5.79 liters with air at a temperature of 22 degrees Celsius. If the football is taken outside where the temperature is 1 degree Celsius, what is the new volume of the football? Assume the pressure inside the football remains constant. Remember, in order for Charles' law to hold true, we've got to have a constant mass of gas at a constant pressure. So let's take a look at what we're given up here. 5.79 liters. And I realize the liters is down here, but that's V1. Liters is an expression of volume. Here's the first temperature we read about in our problem, 22 degrees Celsius. That's going to be T1. Now, bear in mind that that's a Celsius temperature. I'm going to have to do something with it here before I can solve the problem in just a moment. finally, it says, what is the new volume? Okay, so that's our unknown. What are we looking for? We're looking for V2. And here's T2, 1 degree Celsius. Okay, at this point, I've got 3 of the 4 variables that are a part of Charles' law identified. I know I'm looking for V2, so let's write the expression. Okay, V1 over T1 equals V2 over T2. All right, I need to rearrange this, which means I'm going to need to move that T2 out of the denominator on this side. I'm going to need to move it to the other side, and what that involves is multiplying by its reciprocal, and whatever I do to one side of the equation I have to do to the other. All of that's early logic school math. But what it's going to do ultimately is give me this: V1 T2 over T1 equals V2. Okay, there's the rearranged form of the equation that I need. Before I can solve the problem, however, I got to make some temperature changes. Okay, for T1, which is 22 degrees Celsius, I need to convert that to Kelvin. So I'm going to add 273 to that, and that's going to give me a T1 value of 295 Kelvin. Please note that there's no degree symbol associated with the Kelvin scale. T2, this one's pretty easy. T2, 1 degree Celsius plus 273. I think even Dave Turner can get this one right. 274 Kelvin. All right, I've got everything I need, so let's go down here and let's substitute. V1, 5.79 liters times T2. Make sure you use the right temperature here. This is 274 Kelvin. All of that over my original temperature, which is 295 Kelvin, and that's all going to be equal to V2. Now, before I crank out that answer on my calculator, let's remember something about Charles' law. It is a direct relationship between temperature and volume. In other words, whatever one of the variables does, the other follows it. In other words, it does the exact same thing. So if my temperature is going from 22 degrees Celsius down to 1 degree Celsius, that's a decrease in temperature. What must my volume do? Well, it's going to go down. So in other words, before I even punch out this answer on a calculator, I know it's going to have to be less than 5.79 liters. So when I punch out the calculator, I get 5.40 liters. And it turns out, that's 3 significant figures. There's no need to do anything else with respect to scientific notation. So that's a good answer for this first sample problem. Here's our second Charles' law sample problem. Many students have suggested that I am full of hot air. If I inhale 2.2 liters of gas at a temperature of 18.0 degrees Celsius, the air's volume will expand to 2.36 liters in my lungs. What is the Celsius temperature required to accomplish this? Okay, first thing I find here, 2.2 liters. What is that? Liters is an expression of volume. That's the first volume you see in this problem. So that's V1. I'm told that 2.2 liters of gas is at a temperature of 18.0 degrees Celsius. That's my first temperature. Okay. Want to know what the new Celsius temperature is when this gas expands to 2.36 liters. 2.36 liters, that's V2. So I'm interested in a Celsius temperature. Please note, Celsius temperature. Pay attention to that. Okay, so what am I looking for? I'm looking for T2. All right, we've identified our variables. V1 over T1 equals V2 over T2. And I'm going to go ahead and simply get to the rearrangement. I'm looking for T2. The equation is going to end up looking like this. T2 is equal to V2 T1 over V1. That's what the rearranged equation looks like. Once again, I've got to take that first temperature, which is 18.0 degrees Celsius, and I've got to convert it to Kelvin. So 18.0 degrees Celsius plus 273 is going to equal 291 Kelvin. Okay, so T2 is going to be equal to V2. Pay attention to the subscripts. V2 is 2.36 liters, and T1, I just calculated that, that's 291 Kelvin, and all of that's over V1. The original volume is 2.2 liters. Okay, before we crank out the calculator answer, ask yourself what's going on here. Well, I'm going from a volume of 2.2 liters to a volume of 2.36 liters. My volume is going up. What's going to happen, or what's required in order to increase that volume? And if you understand Charles' law theoretically, you know that because it's a direct relationship, if the volume is increasing, the temperature has to increase as well. And so what we find here when we crank this out is a temperature of 312 Kelvin. Now, it's not necessary to put temperatures in scientific notation, but I want you to go back here and look. Notice it says Celsius temperature. This is a Kelvin temperature. In order to convert to Celsius, I'm going to have to take that 312 Kelvin, and I'm going to have to subtract 273 from it, and what I get as a result is 39 degrees Celsius. And that's my final answer to this second sample problem. Okay, here are your two Charles Law practice problems. In the first problem, I ask you to solve for a new volume. And in the second problem, a couple of things here. First, notice that there are volumes given to you in cubic meters. That is an acceptable unit of volume. So don't let that bother you as you make the calculation. Okay? What I'm asking you for in practice problem number 2, though, is a temperature, and not a Kelvin temperature. I'm asking you for a Celsius temperature. So within the problem, you have to utilize Kelvin temperatures. Once you get your answer in Kelvin, then do your subtraction to get the Celsius temperature. Good luck.
Sí.